Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing with our look at derivatives of carboxylic acids. Specifically, we're going to be looking at esters. That is, molecules that form from the reaction of carboxylic acid and alcohols. Now, to be a carboxylic acid derivative, remember a molecule must be able to react with water to generate carboxylic acid. Esters are formed by the reaction of carboxylic acid and alcohol. Water is lost and an ester is formed. Let's take a quick look at the nomenclature of esters. Esters, as shown above, are named by dropping the ic acid ending of the carboxylic acid and adding ate. So you see ethanoic acid becomes an ethanoate, and its common name, acetic acid, becomes acetate. The alkyl group that is attached to the oxygen, singly bound, is named as an alkyl out front of the OH word or root, and that word is separated by a space. Hence you see the molecule as shown here. Now, interesting developments can occur when you have dicarboxylic acids. For example, suppose I have the following dicarboxylic acid. This is a 3-carbon chain, so it's derived from propane, dioic acid. Now, propane dioic acid has the common name malonic acid. What happens if we replace only one of the carboxylic groups with an ester? That is, we have something like perhaps a methyl off of the oxygen. Well, in this case, it is named as if both ends were ester groups. And off of the one ester, we have a methyl. And off of the other one, we have an hydrogen. So it's named as if it's a propane dioate. There's no way of saying propane dioatoic acid. So you have to go with one or the other. And what they chose to do is if there's any ester on a dicarboxylic acid, you drop the ic acid, it becomes a propane dioate. Dioate. Now the question is, what do you do with the rest of the words? Well, what happens is hydrogen is usually named next. It's separate, a separate word out front, and you have a hydrogen. I'm going to run out of room, so I'm going to rub off this name to make some room. Okay, so we have a hydrogen here. And then there's a space, hydrogen, propane, dioate. And a separate word from that is what's off the other hand is methyl. So usually, the way you name this is methyl hydrogen propane dioate. If it's asymmetric, you will use, a likewise malonic acid. Just before we go, malonic acid ends in malonate, and so you'd have methyl hydrogen malonate. All right, now If you had two methyl groups on, the hydrogen's gone now, and so you'd have a dimethyl propane dioate or a dimethyl malonate. What if we had different ester groups? Well, you name both alkyl groups. Let's say we had an ethyl. Then I'd have, I guess I just needed to rub off the M, an ethyl methyl propane dioate, or an ethyl methyl malonate. Note, we alphabetize most of the time. The only time that we violate our alphabetization is actually based on a prioritization methodology. The methyl comes first, or the ethyl. Hydrogen comes right in front of propane dioate. But we can use the alphabetizing method and say ethyl methyl. But usually when there's a hydrogen off of this, you have the alkyl, then the hydrogen, and then the propane dioate. Okay. So there's some nomenclature of esters and diesters. Note, the alkyls are separated from the root name by a space. Okay, so how do we prepare? Let's take a look at the preparation. This preparation of these esters. Now, the most standard reaction is to take a carboxylic acid in the presence of an alcohol, and this time let's use cyclohexanol. Now when you do this reaction, it's often catalyzed by acid. Again, we must use acid and not base. Base would simply deprotonate the carboxylic acid. Acid helps or facilitates the increase of the polarization of the carbonyl, making it more susceptible to nucleophilic attack. We'll look at that in a moment. We apply heat, as indicated by the triangle, and we make our ester. And of course, water is given off with it. This is an equilibrium. Right? Because it's an equilibrium, it's reversible, so if you want to drive this reaction to completion, you often must remove the water. If we take a look at this reaction in terms of relative rates, the less substituted the carboxylic acid, the more reactive it is. And that makes sense, as nucleophilic acyl attack must attack the carbonyl. And so as we add more steric hindrance around the C double bond O, we're less likely to get reaction. Okay, let's just write it this way. HCO2H reacts faster than CH3, CO2H, which reacts faster than R, CH2, CO2H, and so on. As we put more R groups on, we slow down the reaction. And that is greater than R3CCO2H. Now, likewise, the less sterically hindered the alcohol, the faster the reaction. Again, controlled by methanol being faster than a primary alcohol, is faster than secondary alcohol, is faster than tertiary alcohol. Of course, As always, this type of reaction goes through a nucleophilic acyl substitution mechanism. Let's start again and take a look at that mechanism of reaction. I'm going to start with a ethanoic acid. Of course, we're in H+, so H+ protonates the carbonyl, basically increasing the polarity of the carbonyl bond. Does so by resonance. So if I have an H here, lone pair plus on the oxygen, that is resonance stabilized, where the pi electrons move out on the oxygen. Oops, it's an OH. That's an OH. Okay, and so the positive's now on the carbon. And we can now attack. So I can have my cyclohexanol. So I've got HO. My alcohol can attack as a nucleophile now. Okay. If my cyclohexanol attacks nucleophilically, goes for the plus on the carbon, I'll get R, C, OH, OH, O, six-membered ring. Now this H has an H off of it, and this lone pair, and it's positively charged. I can lose a proton. Which will give me R, C, OH, OH, O with an aromatic ring. Notice that if I protonate the oxygen and kick out the cyclohexanol, I'm just going backwards. So going backwards is plus H plus. Going backwards here is minus cyclohexanol. And so far, everything in the equilibrium is reversible. But in acid, you can protonate the alcohol groups. If you do that, you get RCOH. If you protonate one of the OHs on the alcoholic groups or the OH groups, now we've got a good leaving group. We kick out our water, minus H2O. And what does that generate? Obviously, that generates this guy, R, C, OH, O with the cyclohexane ring. And we have a positive charge. Now, this is resonance stabilized, where I can dump in lone pair electrons, create a pi bond either from the oxygen with the cyclohexane or the OH. I could dump it in, and that generates two resonance contributors. So let's draw them. Here's one of them. Plus on that oxygen. So essentially I dumped that in. Or I could dump these electrons in to create a pi bond, move those pi electrons back out to a lone pair. If I do that, I get RCOH, 2 lone pairs. And now I have double bond O with the cyclohexane. Now remember, these are all resonance contributors, plus on the oxygen. And so they can lose H+. If we lose H+ specifically from this structure, it's very easy to see how you form the ester. And this type of esterification, of course, involved nucleophilic attack of the alcohol. So this is a nice example of nucleophilic. We're attacking an acyl group right here. That's an acyl group, nucleophilic acyl. And we did substitution. We added the O-cyclohexane and kicked out the water. So there's substitution. Nucleophilic acyl substitution. All right. Okay, other methodologies for preparing such molecules are available. But one should note that what you cannot do is do this reaction mechanism in base. And the reason is, if we took CH3, C double bond O, OH in base, because carboxylic acid is an acid, even if the alcohol is present, the first thing that's going to happen is you're going to deprotonate the carboxylic acid. Once the carboxylic acid becomes the carboxylate anion, the negative charge reduces the susceptibility of the carbonyl towards nucleophilic attack. But even if a nucleophile could come in and bind to the carbonyl, then you would get a di-negative species, but because there's no protons to protonate, there's no way of generating the good leaving group H2O. In fact, you can't even generate OH minus, and there's no way you're going to kick out an O2 minus. So because base deprotonates the acid, you basically shut down nucleophilic acyl substitution as a reaction pathway. So base cannot do this reaction. Well, what other methodologies are there for the synthesis of esters? Well, we can use acid halide. In fact, we've already covered this a few scribblecasts ago when we looked at acid halide reactions. And if I take a CH3, C double bond O, I'm going to just put X for the moment. You'll see why. In this case, X is a chloride. I'll take methanol as my alcohol. We undergo nucleophilic acyl substitution. So we get addition. And we get CH3, oxygen first, CH3. We have a proton here, lone pair plus, X. We kick out X minus, and we will form CH3, C double bond O, OCH3, and we have an H positive on the oxygen. Often what we do is we throw in a base that's a poor nucleophile to help extract the proton. The base we're going to use is pyridine. Pyridine comes in, it has a lone pair on the nitrogen, so it picks up the proton, becomes an H, or it becomes a pyridinium cation. And so combine that with the X minus, and you end up forming a pyridinium chloride. Once it deprotonates, you've got your ester. Pyridine is a poor nucleophile because the lone pair of electrons on the nitrogen's in an sp squared orbital. It's sufficiently basic to abstract protons, but it's not going to compete with methanol for nucleophilic acyl substitution. So the overall reaction here is methanol plus pyridine. Note in this reaction, you also form the pyridinium salt with the X minus. So in acid chlorides, X equals Cl. And you generate pyridinium chloride. Let's write that down. Pyridinium is also sometimes called pyridine hydrochloride, so we get pyridinium chloride here. And the ester that's formed, of course, is methyl. In this case, ethanoate. Okay. So, we can synthesize esters by the reaction of acid halides and alcohols. What's interesting, and you may be posing the question, is why he placed X here. We can very easily change this to an anhydride reaction and keep the same reaction up. In other words, I just erased this title, make it anhydrides. Now my X becomes some kinds of carboxylate. RC double bond. Oops. Need some more room. RC double bond. O. O. And the X is this type of group. So let's let the R be methyl, for example. If R was methyl, then this would become, that X minus would be a CH3, C double bond O, O minus. Well, that's an ethanoate, so this would be pyridinium ethanoate, or pyridinium, that's an acetate. So we could use the common name, for example. But the reaction is exactly the same. Notice I didn't change a thing in the mechanism. The only thing that changed was the nature of the leaving group. From acid chloride to anhydride, we still use the alcohol. If we use the same alcohol, we get the same product. Exactly the same, which is very amazing. So either acid chlorides or anhydrides both have good leaving groups. Nucleophilic acyl substitution, reaction with alcohols, will generate high yields of ester. Okay, let's try a reaction that would exemplify this. Suppose I gave you the following anhydride. And I said, treat this anhydride with sec-butyl alcohol. Now, pyridine helps, but it's not always required. The carboxylate itself that gets kicked out is weakly basic, and so will abstract the proton as well. So I just need to think about what's going to happen here. The alcohol, remember, acts as a nucleophile, so it's going to go for one of the carbonyls. So essentially what I'm going to do is I'm going to get something temporarily that looks like this. So on scrap paper, I try and figure this out because I'd know I get an O minus, right? And then I'd have my alcohol. I'm going to just put OR, and it'll have an H on it. Well, of course, I know the pi bond reforms. This bond breaks. So I very quickly know in scrap paper that I'm going to get to something like this. Now, because there's no base around, and because I've now got this double bond, OR, H plus. Okay, well what's going to happen is if I got this O minus over here, he's weakly basic. I've got this ester that's protonated. Esters don't like being protonated, wants to give up the proton. That proton's clearly going to transfer over here. And so I finish up with double bond O, OH, double bond O. In this case I have an O attached to a CH, which has a CH3 and a CH2, CH3. Okay, why don't we try to name this? In order to name the ester, I don't try to name the ester. I try to name the original parent acid, but I see an anhydride here. How do I name the anhydride? Well, I name the anhydride from the parent acid. What's the parent acid? Well, all I have to do is split the molecule here, and I can draw the parent dicarboxylic acid. It would look like this. So there's the parent dicarboxylic acid. What is that acid? Well, the IUPAC name for this acid is to name it like an aromatic ring, remember? So it's a benzene with two carboxylic acids, so it's a dicarboxylic acid in the 1,2 position. So this is benzene 1,2 dicarboxylic acid. Or its common name is phthalic acid. Now, if I was to name the anhydride, I could say benzene 1,2 carboxylic, we drop acid and replace it with anhydride. So it's just benzene 1,2-dicarboxylic anhydride or phthalic anhydride. So that's pretty easy, but it takes up room, so I'm not going to put it there. Using this name, these names, how would I name this ester? Well, remember, the ester is named because there's only one ester on. We use the 8 ending. We can't keep ic acid and 8, so we name it as an 8. So this would be a benzene 1,2-dicarboxylate. Benzene 1,2-dicarboxylate. And then out front, we put sec-butyl and hydrogen because we're using sec-butyl alcohol. So we'd have a sec-butyl group, we have a space, and then we have a hydrogen and a space. Or we could say sec-butyl space hydrogen phthalate. Phthalate for phthalic acid. Drop the ic acid and add the 8. Both would be acceptable. All right. Let's take a look at another methodology for preparing esters. We can carry out the nucleophilic substitution of an alkyl halide. So we could make an ester from an alkyl halide. And we saw this when we actually studied SN1 and SN2 reactions of alkyl halides. For example, we could use a carboxylate as a nucleophile. Now, if you remember, carboxylates are very weak nucleophiles. So, because of that, since carboxylates are very weak nucleophiles, we usually use very reactive alkyl halides. If I react this molecule with benzyl chloride, benzyl is extremely reactive because the transition state in the SN2 is stabilized by overlap with the pi bonds, and in the SN1 reaction we get a series of resonance stabilized carbocations, structurally speaking. Since we're using a weak nucleophile, we probably favor SN1 since the benzyl chloride can go either mechanism. You may get SN2 happening. And of course, nucleophilic substitution. First we get the carbocation and then the minus would attack, and so we'd produce a benzyl ethanoate. Another very interesting methodology for preparing esters is to use the molecule diazomethane. Diazomethane is the molecule CH2N2. Let's review, go way back now to the beginning of this course, and draw a Lewis structure, an acceptable Lewis structure for this molecule. To do so, we must calculate the total number of valence electrons. And in that case, we have carbon, which is 4. We have 2 times 1 for hydrogen. And we have 2 times 5 for the nitrogen, which gives me a total of 16 valence electrons. If I do this, I can put carbon with 4, nitrogen with 5, nitrogen with 5. And we can start, hydrogen has 1, hydrogen has 1. We can start linking things up. If we make bonds thusly, carbon wants 8 electrons. If we make a double bond to carbon, we get 2, 4, 6, 8. Carbon's happy. Nitrogen has 2, 4, 6, 7. 2, 4, 6, 8. This nitrogen's happy. 2, 4, 6, 8. But this nitrogen only is 6, so we're going to datively donate these 2. And if we do that, we get this structure. If I do formal charge, carbon 0. This nitrogen's plus 1. 5 minus 4. This 5 valence electrons minus 2, 4, 5, 6. 5 minus 6, this guy's minus 1. Now I can draw a series of resonance contributors for this molecule. Okay. I can, for example, move these pi electrons out on carbon. If I do that, I get an H, an H, lone pair here. Nitrogen's now electron deficient. We get a 2 plus. We get a 1 minus. And we still have a minus 1 here. So this clearly is a minor contributor with greater charge separation. I can fix that somewhat by dumping these pi electrons in. If I do that, I get an N, triple bond, N. 1, 2, 3, 4, 5. 5 minus 5, 0. Plus 1. We have a lone pair here, minus 1 here. Clearly the major contributor is this guy, A, followed by, in this case, C, B. B would be a minor contributor because of the greater charge separation and the fact that you only have 6 electrons around the nitrogen. Okay, so there's the molecule diazomethane. How can we prepare an ester from this type of molecule? Well, the way to do that would be to react it with carboxylic acid. Suppose I threw in some acetic acid. If I look at these resonance contributors, I can guess what would happen. Acids are good sources of H+, and one of, albeit a minor contributor, structure C, has a lone pair in carbon, which is fairly basic. I could envisage protonating this and generating this unit. H, H, H. A CH3 with an N triple bond N. And of course, it's positively charged with positive charge on nitrogen. Now, what you generate from this, of course, is once the acid's deprotonated, it becomes a carboxylate, which is a weak nucleophile. The protonated diazomethane has an excellent leaving group, and it's excellent because the N2 gas that will eliminate the N2 molecule is a very weak base and a super powerful leaving group. And so, even with a weak nucleophile, this is very reactive. and you'll kick out N2 gas. So minus N2 gas, bubbles out of solution. And what you end up with is CH3, C double bond O, you carboxylate, but off of the oxygen is a CH3. This came from the diazomethane. If you think about it, it's as if the CH2 inserted in between the oxygen and hydrogen of the carboxylic acid. And so diazomethane, right, if you wanted to show the overall reaction, you'd write it this way. And it actually looks like you're putting a CH2 between the O and the H of the carboxylic acid. So the overall reaction would look like this. Arrow, CH2N2. Okay. And it looks like that CH2 goes in between the oxygen and the hydrogen. Okay. So, compared to the other carboxylic acid derivatives, the preparation of esters seems much wider and varied. I'm Dr. Brian Lloyd. This is my Scribblecast, and thank you for listening.